Hello everyone, Mr. Fawcett here, and we're back with another geometry lesson. Today we're going to talk about the properties of special parallelograms. So the last two videos we've talked strictly about just different parallelograms, what makes a quadrilateral a parallelogram, and what the properties of different parallelograms are. And now we're just going to look at some of the special ones. Before we get going though, start with this do now. We are told that ABCD is a parallelogram, and you need to find each measure. So the length of segment CD and the measurement of angle C. So go ahead, pause the video, and then join back in for a discussion. Okay, so let's start with sides first. Might be a little bit easier. If this is a parallelogram, then I know that opposite sides are congruent. So I could say that 5y minus 1 is equal to 2y plus 8. Then I get 3y minus 1 is equal to 8. I get 3y is equal to 9. I get y is equal to 3. Just be careful, this is not what they're asking you for. You do need to find the length of CD. So CD is equal to 2 times y, or 2 times 3 plus 8. CD is then equal to 14. Okay, let's take a look at these angle measurements. If it's a parallelogram, because we have these parallel lines, right, or parallel segments, well, these two angles are consecutive interior. And we already, the shortcut is just saying consecutive angles in a parallelogram are supplementary, but this is the reason why, right? It's because parallelograms have parallel lines. So I get 16x minus 4 plus 14x plus 34 is equal to 180. That's going to give me 30x plus 30 equals 180. That's going to give me 30x is equal to 150, and that's going to give me x is equal to 5. Now again, I'm finding the measurement of angle C, and I know that in a parallelogram, opposite angles are congruent. So the measurement of angle C is equal to the measurement of angle A. So the measurement of angle C is equal to 14x, or 14 times 5, plus 34. That's going to be 70 plus 34, which is equal to 104 degrees. So just a little review problem dealing with the different properties of parallelograms. Okay, let's move into our first special parallelogram. We're going to work with a rectangle. So a rectangle is a parallelogram. So it has all the properties we have previously discussed about parallelograms. However, a rectangle also has a couple of unique properties of its own. Specifically, a rectangle is a quadrilateral with 4 right angles. That is the definition of a rectangle. So the theorem we're going to look to prove here is that if a parallelogram is a rectangle, then its diagonals are congruent. Okay, so diagonal AC should be congruent to diagonal BD. So again, pause the video, see if you can come up with the correct reasons here to prove this theorem. Okay, so we are told that ABCD is a right angle, and that would let us know that angle BAD and CDA are right angles, right, by the definition. So definition of a rectangle. If angle BAD and angle CDA are right angles, well, then they have to be congruent to each other. And I'm trying to think if we've actually ever used this in a proof before. We may or may not have. But if I know that two angles are right angles, then we have this theorem called the right angle congruence theorem, which says that if two angles are both right angles, then they are congruent to each other. So you may not have known that one, and that's okay. It's not been one that we've used consistently before. But jot that down, the right angle congruence theorem. If two angles are right angles, then they must be congruent to one another. Okay, how do we know that ABCD is a parallelogram? And at first it may seem like there's not a reason here, right? You're trying to think of, okay, what property have I shown to prove that this is a parallelogram? All we've really proven is that this angle right here is congruent to this angle right here, and that doesn't seem like it's enough to prove that that entire figure is a parallelogram. And you're right, it's not, except that we know that the entire figure is a rectangle. And rectangles are parallelograms, right? They're a specific type. So here we can just say rectangles are parallelograms. All right, if something's a rectangle, you can go backwards and say that it also must be a parallelogram. Obviously, the reverse is not true. Not every parallelogram is going to be a rectangle. Next statement says segment BA is congruent to segment CD. So I've got BA congruent to segment CD up here in my diagram. Well, if I know that a figure is a parallelogram, opposite sides of a parallelogram are congruent. Center this. There we go. This is something that we've proved in a previous video, right? It doesn't have a special name, so if you're using this theorem, this is what we can say, right? And you could write out the entire theorem if you wanted to. If a figure is a parallelogram, then opposite sides are congruent, or you could just shorten it to this. Next statement says AD is congruent to AD. Well, that one should be an easy one. Reflexive property of congruence. Again, you can say POC or property of congruence, either one is okay. And then it looks like we have enough to prove that these triangles are congruent. So it may not be the ones you're thinking of though. Make sure you read the letters carefully. BAD is congruent to triangle CDA. So they do overlap. This is going to be due to SAS congruence. You may have thought it was HL because both of those triangles have right angles. However, the hypotenuses are not congruent here. Both the legs are, and the angles in between the legs. So this is going to be SAS. If we know that these triangles are congruent, we can say that corresponding parts of these triangles are also congruent, like BD. So we've got BD, that's the, oops, let's do that in pink. I'm going to do it like this. Segment BD is going to be congruent to segment AC, which both of those are the diagonals of the rectangle, right? So we have just proven that the diagonals of the rectangle are congruent. Of course, this is CPCTC. So if we have a rectangle, the rectangle's diagonals will be congruent to one another. They will have the same measurement. All right, on to the next one. I believe I only have 3 for us today, 3 proofs. Two and 3, yep, 3. Okay, let's see what we're going to do with this one, because it's a little bit too big to fit on one page. Might have to shorten these a little bit. All right, we have just done it. So we're now going to look at the properties of rhombi. Rhombi is just the plural form of rhombus. So a rhombus is a parallelogram. So it has all the properties we have previously discussed about parallelograms. However, a rhombus also has a couple of unique properties of its own, just like rectangles. Specifically, a rhombus is a quadrilateral with 4 congruent sides. So if a quadrilateral has 4 congruent sides, we can put it in the rhombus category. The theorem that we are trying to prove here is that if a parallelogram is a rhombus, then its diagonals are perpendicular. So we want to prove that these diagonals are perpendicular. Go ahead, pause the video, see if you can fill in those statements, and then come back and see how many you got right. Okay, first one is obviously given. ABCD is a rhombus. Then we are told that all four of these sides are congruent. BA, AD, DC, and CB. And that is the definition of a rhombus. That's what we looked at above. ABCD is a parallelogram. Well, this is kind of like our previous proof, right? If something is a rectangle, it has to be a parallelogram. Same with a rhombus. Rhombi, or you could say a rhombus, is, well, in this case I'm using plural, so I would say are parallelograms. If something is a parallelogram, then we know that the diagonals bisect each other. And BD and CA are diagonals. Do one in red, one in blue. And if those bisect each other, well, we'll come to it later, but I know that BE is going to be congruent to ED, and AE is going to be congruent to EC. However, going back to this reason, right, if something is a parallelogram, or if a figure is a parallelogram, then the diagonals bisect each other. And that's just what we're going to say. We're going to say diagonals of a parallelogram bisect each other. This is a theorem that we proved in an earlier video. It just doesn't have a special name. So if you want to write out the entire theorem, you can. If a figure is a parallelogram, then its diagonals bisect each other, or you can just shorten it to what I have on the screen. The next statement deals with what I just talked about with the diagonals. So it says segment BE is congruent to segment ED. Those are the red two tick marks. And that's just going to be definition of segment bisector. Right, we have a segment being bisected, so both pieces of that segment will be congruent. The next statement says that segment EC is congruent to segment EC. Well, that's going to be due to the reflexive property of congruence, or reflexive POC. So it turns out we actually, for right now, we don't actually need to have these congruency tick marks on there. It doesn't hurt to have them. We're just not going to be using it for the next few lines of our proof. The next line says triangle BEC, let's do that in pink, BEC is congruent to triangle DEC. We'll do that in orange. So those two triangles are congruent because of SSS congruence, triple S. Okay, if we know the triangles are congruent, angle BEC congruent to angle DEC right here due to CPCTC, right? Corresponding parts of congruent triangles are congruent. Well, if I know that those angles are congruent, I know that their measurements have to be equal by the definition of congruent angles. The next line may not be related to the previous line. It says measurement of angle BEC plus the measurement of angle DEC. So again, those two angles that I have marked off in brown are equal to 180 degrees. Well, we know that they're congruent, but why would they be equal to 180? Well, they are a linear pair, right? So this would be linear pair theorem. If I know that they're congruent and I know they're equal to 180, well, this next line, they've done some substituting, right? They took, because the measurement of angle DEC is equal, I was not really showing you what I wanted to do there. Because the measurement of angle DEC is equal to the measurement of angle BEC, right? these two can be used interchangeably. So they made a substitution here, substitution property of equality, or POE. And then they simplified. And then they divided both sides of that equation by 2. Well, if I know that the measurement of an angle is equal to 90 degrees, I know that the two segments or sides or lines that form that angle have to be perpendicular by the definition of perpendicular. Oops, there we go. And BD and AC, right, those are the diagonals of the rhombus, so we've now proved that those diagonals are perpendicular. So we've proved the theorem we wanted. If a parallelogram is a rhombus, then the diagonals are perpendicular. All right, let's move on to our final theorem of the video. A little bit shorter than the last one. Let's move this all on to the next page, though. There we go. So we are going to prove that if a parallelogram is a rhombus, then each diagonal bisects a pair of opposite angles. So if a parallelogram is a rhombus, then each diagonal bisects the opposite angles. Again, stop the video, try this on your own, and then join back in for our final discussion. Well, the first statement is given. Same thing as last time. They're now saying that all 4 sides are congruent. And we know this because this is a rhombus. So definition of a rhombus. XV is congruent to XV. That would be a reflexive property of congruence. Triangle WXV, let's highlight that in pink. Triangle WXV is congruent to triangle YXV. And I guess we should put these tick marks on the reflexive property right here. So those two triangles are going to be congruent, again, by SSS. We have 3 sets of congruent sides. Okay, then we are told that 2 sets of angles are congruent. So we've got angle WXV is congruent to YXV. And then we have WVX is congruent to angle YVX. And again, if we have 2 triangles that are congruent, corresponding parts of those congruent triangles are congruent, so CPCTC. If I know that the angles are congruent, I know that their measurements are going to be equal. Definition of congruent angles. And our last statement says that XV bisects WXY and WVY. So let's again try to figure out why we're allowed to jump there. And it has to do with what's going on right here. We are told that the measurement of WXV is equal to the measurement of YXV. Right, so these 2 angles up here, those 2 have the same measurement. Well, if they have the same measurement, that angle is being bisected. Likewise, down at that other vertex, V, oops, let's get on my pen tool. If these 2 angles have the same measurement, then that angle V has been bisected, right? Because each half is actually a half. They'll have the same measurement. So this is just going to be definition of angle bisector. If you prove that both of the smaller angles that make up the larger angle are equal, then you know that that angle is being bisected. Definition of angle bisector. So we've proven that if a parallelogram is a rhombus, then each diagonal bisects a pair of the opposite angles. Now, I will say, if you were writing this proof on your own, I would accept it if you had not included this line. Because based on the definition of angle bisector, you can say that the angles are congruent if they're being bisected, right? Or you can say that they have the same measurement. So that means you can go the opposite way as well with just saying that the angles are congruent. So if you can prove that each, right, and that's what we have up here with the tick marks, right? If you can prove that each of the smaller angles are congruent, then you can jump right to those angles being bisected. Sometimes I do throw in extra things just to see if you remember, extra properties. But if you wanted to shorten your proof and still have it be correct, you could disregard this line. It doesn't make your proof wrong if you include it, it just makes it a little longer. So either way would be acceptable. Take a little note. We only proved that one pair of opposite angles was being bisected, right? We could write another proof in the same similar fashion. Let's just say I had redrawn this diagram, but I had put my diagonal going this way, right, across from V and Y. Well, I could run through the same steps to prove that these angles are also being bisected, which means that that diagonal would also bisect those angles. Again, for sake of time, for sake of space, we're just going to prove it one way. Just note that you could also do it the other way. And if you wanted to, you could go work it out on your own on a separate sheet of paper using the different congruent triangles to do that. That is going to wrap it up for this video. During class, we are going to work on, again, applying some of these different properties and theorems, but hopefully you understand why they work after running through those proofs. Okay, as always, enjoy the rest of your day, and we will look forward to seeing you next time.